in the world is severely limited. Mathematics makes us better in some of the same ways written language does. But mathematics goes beyond everyday language because it is a language that can do real work. The mechanics of mathematics, the rules for rearranging, substituting, and expanding its symbols, are not arbitrary. They are a systematic way to export the process of thinking to paper or machines. Alfred Whitehead, a revered 20th century mathematician whose work we will encounter in Chapter 3, has been paraphrased as saying, "The ultimate goal of mathematics is to eliminate any need for intelligent thought." Given this useful feature of mathematics, some scientific subjects, physics chief among them, have developed an ethos centered on rigorous quantitative thinking. Scientists in these fields have capitalized on the power of mathematics for centuries. They know that mathematics is the only language precise and efficient enough to describe the natural world. They know that the specialized notation of equations expertly compresses information, making an equation like a picture. It can be worth 1,000 words. They also know that mathematics keeps scientists honest. When communicating through the formalism of mathematics, assumptions are laid bare, and ambiguities have nowhere to hide. In this way, equations force clear and coherent thinking. As Bertrand Russell, a colleague of Whitehead, whom we will also meet in Chapter 3, wrote, "Everything is vague to a degree you do not realize till you have tried to make it precise." The final lesson that quantitative scientists have learned is that the beauty of mathematics lies in its ability to be both specific and universal. An equation can capture exactly how the pendulum in the barometrical clock on the minister's landing at Buckingham Palace will swing. The very same equation describes the electrical circuits responsible for broadcasting radio stations around the world. When an analogy exists between underlying mechanisms, equations serve as the embodiment of that analogy. As an invisible thread tying together disparate topics, mathematics is a means by which advances in one field can have surprising and disproportionate impacts on other, far-flung areas. Biology, including the study of the brain, has been slower to embrace mathematics than some other fields. A certain portion of biologists, for reasons good and bad, have historically eyed mathematics with some skepticism. In their opinion, mathematics is both too complex and too simple to be of much use. Some biologists find mathematics too complex because, trained as they are in the practical work of performing lab experiments and not in the abstract details of mathematical notion, they see lengthy equations as meaningless scribble on the page. Without seeing the function in the symbols, they'd rather do without them. As biologist Yuri Lazbenik wrote in a 2002 plea for more mathematics in his field, "In biology, we use several arguments to convince ourselves that problems that require calculus can be solved with arithmetic if one tries hard enough and does another series of experiments." Yet, mathematics is also considered too simple to capture the overwhelming richness of biological phenomena. An old joke among physicists highlights the sometimes absurd level of simplification that mathematical approaches can require. The joke starts with a dairy farmer struggling with milk production. After trying everything he could think to get his beloved cows to produce more, he decides to ask the physicist at the local university for help. The physicist listens carefully to the problem and goes back to his office to think.